Hi, in this video, we want to look at the concept of thermal expansivity. During the course of the video, we'll be looking at the meaning of thermal expansivity, we'll be looking at the applications of thermal expansivity in solids. We'll talk about the types of expansivities that we have, that is the linear expansivity, the areal expansivity, and also the volume expansivity. Then we look at the relationship between these three expansivities and some questions underneath them. Then in the subsequent video, we look at the application of thermal expansivity in liquids. Now, let's move on to what we have for the day. What is thermal expansivity? By now, we know that another word for thermal means heat. And then expansivity is just coming from the word expansion. So when something is expanding, that is when you are increasing in size. Increasing in size. So we can now refer to thermal expansivity as just the increase in size or shape of an object when it is applied to it. Of course, when we're looking at the concept of it from the very beginning, we're told that we have several effects of it. One of the effects of it can lead to a change in temperature, since we define it as the total internal energy present in that body system coming from the kinetic molecular theory of matter. Then, if we apply it to that same body, one of the evidence or one of the effects will be that the temperature would rise. Another effect of it could be the change in physical property. It could also be the change in its chemical property. And then we also have, we have several effects of it. Expansion is an effect of it. That is when you heat a substance, whether it is solid or liquid or gases, it is going to expand. By how much it expands is what we now want to find out by looking at the concept of thermal expansivity. Now, before we delve into the types of thermal expansivities that we have in solids, we need to note that expansion occurs the least in solids. Expansion occurs the least in solids, then followed by liquid, then followed by gases. So expansion occurs the least in solids, followed by liquid, then followed by gases. So it must mean that expansion occurs the most in gases. That is, if I will supply 50 joules of energy, of heat energy to a solid substance, a liquid substance, and a gas substance, the gas will expand more than the liquid, and the liquid will expand more than the solid. And why is that? It's because for solids, the intermolecular forces or force of attraction between two atoms are stronger than that of liquid and stronger than that of gases. Think of this like a block of mass. We were told from primary school and junior secondary that all matters are made up of atoms, and inside of those atoms we have our electrons moving vigorously. And these electrons are tightly packed together. That is, between one atom and the next atom and the next atom, there's this force of attraction they feel. So for solid, because these atoms are tightly packed together, intermolecular forces are way stronger. For liquids, they're not tightly packed together, they're still packed together, but not tightly packed together. That's why they can flow over each other easily. And why for that of gases, the intermolecular forces are weakest in gases, hence the reason why it expands more than the other states that we have. All right. Now, for us to understand the types of expansion that we have, let's try to look at the material, the solid material now. I want to try to look at the solid material. So let me clear this. Okay. So imagine I were to apply it on this material alone. I already know that by the time I apply it to a solid material, not as much as the expansion won't be much. Definitely there will be some form of expansion. So if I apply it to a material that I'm only concerned about its increase in length, that is, initially my length is L0, This is my original length. Then after applying it to this substance, then my length increases. Let's say to this factor. So this is my LF. So where L naught simply means original or initial length, and LF means final length. Now, if only my length is increasing, then the type of expansivity that accounts for this type of increase is what we refer to as linear expansion. Linear expansion. Linear expansion. So why is it that we're saying linear expansion? Because only one side is increasing. Either the length is increasing, or the height is increasing, or the breadth is increasing. In as much as we're only looking at expansion on just one part, then we're referring to linear expansion. And how do we define this? This is simply the change in length per unit length per degree rise in temperature. I repeat myself. Linear expansion is defined as the change in length per unit length per degree rise in temperature. And mathematically, we say alpha must be equal to change in length divided by the original length times the temperature change. So again, linear expansivity is simply the change in length per unit length per degree rise in temperature. Now, for this formula we are given, sometimes you may be asked to find the final length, sometimes you may be asked to find the original length, sometimes you may be asked to find the final temperature. So let me write it as final temperature. Sometimes you might be asked to find the initial temperature. Sometimes you might be asked to find the fractional change in length. As far as linear expansivity is concerned, all you simply want to do is to come to this formula and make the unknown, what you're actually looking for, the subject of the formula. What do I mean? If I want to rewrite this formula, I can rewrite this formula and say alpha is equal to change in length must mean, for physics, must mean final length minus initial length. So I can say LF minus L naught all over L naught. Then changing theta also must mean final temperature minus initial temperature. So whichever one you are looking for, if you are looking for LF, just make LF the subject of the formula by cross multiplying. Then LF will just have to be LF will just have to be, so we have LF minus L naught is equal to alpha L naught. Okay, changing theta. If I want to write this as changing theta instead of theta final minus theta initial, and looking for LF, so LF becomes L naught plus alpha L naught changing theta. If I factorize, I have L naught in the bracket of 1 plus alpha change in theta. So if you're looking for the final length, you want to know by how much increase your new metal will be after subjecting it to a form of heat, then you can come here and use this formula. Sometimes the question might be asking for the final temperature or the initial temperature or even the linear expansivity. Just know how to work your way around these formulas, and then you know how to find what it is you are looking for. So alpha, the unit of alpha is the, either we say per Kelvin or per Celsius. The reason why we use Kelvin or Celsius interchangeably in this topic is that the fundamental intervals for both Kelvin and Celsius are the same, which is 100 and 100. So it doesn't really matter whether it is per Kelvin or per Celsius. So by the time you are given a temperature, you'll be given a temperature change. It can be in Kelvin, it can be in Celsius. So you take it to mean the same thing. All right. So this is that for linear expansivity. So I guess we should just take a question and see how we solve questions concerning linear expansivity. All right, so for our first question, we're told that a rod of initial length 2 meters at a temperature of 25 degrees Celsius is heated to 80 degrees Celsius. Calculate the length or the increase in length of the rod if its expansivity is 4.0 times 10 to the power of minus 3 per Kelvin. The first thing we want to do is to note what we are given. So from the start of the question, we know we are given the initial length to be 2 meters. Then the initial temperature, temperature 1, is 25 degrees Celsius. The final temperature is 80 degrees Celsius. Then one has to calculate the increase in length, or otherwise known as the change in length. So what do we know? We know that alpha, okay, I think we're given alpha 2, if its expansivity is 4.0. So alpha we're given to be 4.0 times 10 to a power of negative 3 per Kelvin. Now, before you want to say, okay, the temperatures are given in Celsius and then the expansivity or the linear expansivity is given in per Kelvin. So again, it doesn't matter because we're dealing with the fundamental intervals here. So they have the same fundamental intervals. Pick a unit of temperature and stick with it. So we know that from our formula, alpha is given as change in L over initial length, then times temperature change. Now, how do we get temperature change? By simply taking the final temperature and subtracting it with the initial temperature. So we have 80 minus 25. And 80 minus 25 gives us 55 degrees Celsius. Now, we've gotten our change in temperature. We know our initial length. We're looking for the change in length. We know our linear expansivity. So we can simply cross multiply. So change in length becomes alpha times L naught change in temperature. So now we can impute our values 4.0 times 10 to a power of negative 3 multiplied by the initial length is 2 meters, then multiplied by 55. So this will be equal to, so let me quickly get my calculator, 4.0 times 10 to a power of negative 3 multiplied by 2 multiplied by 55. So our change in length is 0.44 meters. So what this simply means is, imagine this were to be my rod length 2 meters initially, then I apply it to this, then it expanded to 2.44 meters. So when you apply it to this. So this is how we solve a typical question on linear expansivity. So moving on to the second type of expansivity that we have, that is the areal expansivity. So for area expansivity, we also call it the superficial expansivity. What exactly does it mean? When we're talking about the linear expansivity, we said we had a metal that has a length, but this time around, my metal won't just have a length, it will have a length and also its breadth. Think of it as a 2D shape. Huh? Now, the shocking thing, or one thing we should note about solid expansion is that it is uniform on all sides. That is, if the length is increasing by a factor of 2, the breadth also should increase by that same factor. I guess we can look at it in this way for it to make sense. Imagine this is 2 meters, just like the last example we treated. Now, when we change the, what's it called, the temperature of my metal, so let's say I increase the temperature by 10 degrees Celsius or 10 Kelvin. So maybe initially I had a temperature of 10 Celsius. Then after a while, maybe I increase the temperature to 20 degrees Celsius. So I increase the temperature by a factor of 10. Let's say my length, my change in length will be 0.4. So that means my new length here should be 2.4 meters. Now, if I were to increase the temperature by another 10 degrees Celsius, say my new temperature is 30 degrees Celsius, then this length I can predict it. It will be approximately 2.8 meters. The change in temperature is uniform. But what if we're not dealing with just the length now, and then we have the length and the breadth? So how then do we want to calculate the expansion? How do we want to know by how much the object or the solid has expanded? Hence the areal expansivity or superficial expansivity. Now, as the length is increasing, so also is the breadth in the same proportion. So we can now say, in the previous one we used alpha, so for this one we're going to be using beta, just like it is used in majority of your textbooks. So superficial or area expansivity is now the change in area per unit area per degree rise in temperature. So what I'm basically saying is, sorry about this, okay, change in area per unit area, that is the original area, then times the change in temperature. So imagine this solid has an area A1. So when it was, let's say, 10 degrees Celsius, by the time I apply it to this, what happens? The length increases, the breadth also increases. So this increase, this change in area that has increased is what we've written here. And remember, we can also say beta must be equal to A final area minus the initial area divided by the initial area times the temperature change. Again, temperature change can be written as final temperature subtracted by initial temperature. So depending on what we are looking for. Now, peradventure, we are being asked to calculate the fractional change in area. Fractional change in area will simply be the change in area divided by the original area. So what we simply want to do is to make change in A over A naught the subject of the formula in this equation. So what do we want to do? So we can do that step by step. And this is true for linear expansivity also. I'm stressing this out because I failed to mention it when we're talking about linear expansivity. So if I want to find the fractional area, so what do I want to do? You can start by cross multiplying this. Cross multiplying this, we'll have beta or the superficial expansivity multiplied by A naught, that is the original area, multiplied by the temperature change must be equal to the change in area. So divide both sides by the original area, then delta A all over A naught, which is the fractional change in area, must be equal to beta change in temperature. So the fractional change, you can see, is directly proportional to the superficial expansivity, also directly proportional to the change in temperature. So by virtue you're being asked to calculate, or maybe you're given the fractional change and you don't know what to do, so this is how you want to write your formula. Sometimes you'll be asked to calculate the fractional change in length, or fractional change in area, or fractional change in volume. So this is what they mean by that. Of course, if they don't ask you to do that, they might want you to find the original area, or the initial temperature, or the final temperature, or the superficial expansivity. Now, since this has to do with area, and from what we just said, the length and then the breadth are increasing in the same proportion. That means we must say that the relationship between my superficial expansivity and my linear expansivity will simply be beta, just being a case of 2 alpha. Assuming that we're dealing with a cube, that is, they have equal length. So the L here is same as the L here. By the time we expand this, we'll see that beta will be equal to 2 alpha. All right. Now, what if we want to talk about the third type or third part of expansivity? The third part of expansivity, that is the volume expansivity, or also known as the cubic expansivity. So this time around, we're not dealing with a 1D shape or a 2D shape, but a 3D shape. So let's say we have a box like this, and then we want to apply it to this box and see how it changes. So originally this box has an initial volume. So let's say it has an initial volume of V naught. V naught at, let's say, 10 degrees Celsius. By the time I apply it to this also, the box will change to expand. So if you want to find out by how much it has expanded, then we are talking about the cubic expansivity or the volume expansivity. And how do we define that? We simply define that as the change in volume per unit volume per degree rise in temperature. And this time around, we denote our cubic expansivity or volume expansivity is gamma. So gamma is equal to the change in volume per unit volume per degree rise in temperature. So we can see that for both linear area and volume expansivity, they all have the same definition. The only thing changing for linear, we talk about only length. For area, we talk about length and breadth. While for volume, we talk about length, breadth, and also height. So for volume, again, it is the change in volume per unit volume per degree rise in temperature. And whether my linear expansivity, the cubic expansivity or area expansivity, they all have the same units. That is the per Kelvin or the per Celsius. Now, the relationship between cubic expansivity and linear expansivity is given as so gamma would now be equal to either we say 3 alpha, but remember, we already said beta is the same thing as saying 2 alpha. So if we make alpha the subject of the formula here, we can say alpha is the same thing as saying beta over 2. So that means for gamma, if we know the area expansivity, we just need to apply this. So we can say 3 beta over 2. So it's to give me my cubic expansivity. So no matter what it is you are looking for, you can substitute this and then look for how to find what's it called, the missing quantity that you're looking for. Now, we should note, of course, we'll stress this more in the next video when we talk about expansion in volume, in liquids rather. Now, for liquids, all types of liquids, liquid undergo only volume expansion. Liquids undergo only volume expansion. That's because liquids don't have the natural shape. That shape depends on the container, and before the what's it called, liquid can expand, the container has to expand first, then before the liquid expands. And most containers are in three what's it called, are in half volumes. So let's not talk about the 1D, 2D, or 3Ds. So they have volumes, and then apparently we can now say that the only type of expansion that applies to liquid has to be the volume expansion. But for solid, we have the linear, we have the areal, and we have the cubic expansion. Now let's solve more questions concerning this and see how we apply all these things to solving questions underneath expansivity. All right, so for our question, we're told that the area of a square metal is 600 millimeters square. We have to calculate its new area when its temperature is raised by 15 Kelvin, and then the linear expansivity of said metal is 1.9 times 10 to the power of minus 5 per Kelvin. All right, so this question basically deals with the relationship between linear and areal expansivity. So how do we solve questions like this? First of all, we start with writing what we know. The original area of my square metal before we apply it to it is given as 600 millimeters squared. Okay, now we have to find the new area, calculate the new area, that is the final area now, not just the what's it called, the change in area, but has to calculate the final area. So final area, we're given the change in temperature. Sorry about this. Change in temperature is given as 15 Kelvin, and then linear expansivity of metal is given as 1.9 times 10 to the power of minus 5 per Kelvin. So like I said, the first thing we want to do is to look for, okay, so let's write our formula. So formula beta is equal to change in area over original area, then times temperature change. Can we get this? Definitely we can. Can we get this? Yes, we can. We are given already. Are we given this? Yes, we are. Now, what is left? Change in area. But it is not change in area that they want us to find. They want us to find the new area. They want us to find the new area. So when we find the new area, we're simply going to come and add it to the old area. So that will be the length of the new area. So what do I mean? Imagine I have a box like this that has this area 600. Now, if I'm looking at delta A, that is, I just want to know by how much. Let's assume that it's increased by this factor. By this factor here, it's increased like, okay, so let me listen. So this is 600. Then let's say the new length, the new area is now this. Now, what this change in A simply means, if the original area would be something like this, would be something like, what's it called? Something like this. But remember, the length increases, the breadth increases. So this is the new area. So this shaded part here is simply my change in area. This change in area here, that's the shaded part here. But for me to get the new area, that is the total area here, everything shaded, then I have to add this change in area to the original area for me to get the new area. Calculate its new area when its temperature is raised by 15 Kelvin. So I hope this makes sense so that when we are solving, you would know why we are doing exactly what we are doing. Okay, so now, first of all, let's try and get B. So beta will simply be 2 alpha, that is, multiply this by 2. So that's 2 times 1.9 times 10 to the power of minus 5. And 2 times 1.9 simply give us 3.8. So it should be 3.8 times 10 to the power of minus 5. So that's my superficial expansivity. So I can cross multiply now. Cross multiplying, I'll have 3.8 times 10 to the power of minus 5 multiplied by the original area, that's 600. Okay, then multiply by the temperature change, which is 15, and this must be equal to change in area. How do I get 3.8 times 10 to the power of minus 5? I simply multiply 1.9 by 2. Why did I multiply it by 2? Because we already said the relationship between linear expansivity, superficial expansivity, and volume expansivity is given by 2 alpha or 3 alpha, depending on which one we're looking for or at. Okay, so delta A will now be equal to, so multiplying this using my calculator now, so 3.8 times 10 to the power of negative 5 multiplied by 600 multiplied by 15. So we have my change in area is 0.342. That's my change in area. But remember, change in area is simply as saying final area minus initial area. So is equal to change in area. So what am I looking for? I'm looking for the final area. So I can simply say final area will simply be change in area plus original area. So that's where we got that from. So just add this to what's it called? Add this to 600, and then we have my original area or my final area becomes 600.342 mm squared, and then we are done with this. I hope this makes sense, like the concept of thermal expansivity. So look at it as or like an effect of it. When you apply it to a substance, it increases in length, and then when you remove it from a substance, it contracts or decreases in size. And then we've been able to look at the meaning of linear expansivity, how to define them. We've been able to look at the concept of area expansivity and how to define it also. Then finally, cubic expansivity and how to define it. So for more contents like this, you can do well to like channel, subscribe to the videos, or like the videos rather, subscribe to the channel, and then also use the description box. So if this is still not clear, we can solve more example questions for you. So in our subsequent video, we'll talk about expansion or thermal expansivity when we apply that to liquid. Thank you very much, and bye-bye.